Okay, welcome back. So let's get into point estimation, which you know, point estimation is a statistical term, and we, as physicists, rather talk about fitting. So you have some data, you have a model. The model has some parameters. You estimate the parameters by fitting the data to the model. That means adjusting the parameters such that they best interpret the data that you have. And that allows you to estimate the parameters of the model. So what you do is you do the point estimation. So you assign a value to each parameter. And the other side of it is combining measurements. Because you might already have done the fitting and you have extracted a measurement of your quantity of interest, the top quark mass. And then the other experiment across the ring has also done the homework and they have their own measurement of the top quark mass. And you combine the two measurements into one. That is presumably, not always, a better estimate of the unknown physical value. So that's what we do, but it's all point estimation in statistics, okay? And then the other big part of it is, interval estimation. That is in statistics all another matter and probably also more complicated because interval estimation is assigning an uncertainty to your point estimate. Okay, so we fit some data, we get a value and an uncertainty. But for statisticians, there are two different problems. The estimate of the central value and the estimate of the uncertainty you can assign to the central value estimated. So let's talk about point estimation, which is assigning a value to the parameter. And let's leave alone, although we of course will talk about it throughout anyways, the interval estimation. Because when we do point estimation, we will also talk about the variance of the estimates, etc. But interval estimation rather is, yes, I have a variance, but how well does it cover the true unknown value of the quantity I'm estimating? So a whole other world of questions comes in. So now we talk about point estimation. We are very often in the situation that we need to combine measurements. And the trick here arises when the measurements that you are combining are somehow correlated among each other. What does it mean for two measurements to be correlated? Well, they might be sharing some data. So for instance, I have 4 data points and this other guy has 2 of my data points plus 3 more. And I make an estimate, he makes an estimate. The two measurements talk to one another because there are some data in common. I also have some data that he hasn't seen, and he has some data that I haven't seen, but there is a crosstalk. But more often, the case is that the measurements talk to one another because they have some correlated systematic uncertainties. So for instance, Atlas and CMS measure the top quark cross-section. They count how many top quarks they see, and they will rely on the rate of protons that collide. And this number is roughly, not exactly, but roughly the same as the number of protons that collide in the Atlas experiments. So I'm in CMS, I see a certain rate of collisions. Atlas sees a similar rate of collisions. And we have an uncertainty. I have an uncertainty of about 2.1%. I have an uncertainty about 2.3%. But most of this uncertainty is correlated. So the uncertainty that we will have on the cross-section and the measurement itself that I get and that they get will somehow talk to one another. So these kind of issues are commonplace, and they are the hardest to deal with because they produce problems that are rather tricky, as we will see in very simple examples too. So we should become familiar with these issues because for us, for particle physicists, this is our daily job. Okay, this is how we earn a living. All right. So, so we said it. Parameter estimation in statistics is divided in point and interval estimation. So the issues of combining different estimates of the same parameter is in itself a particular case of data fitting, because it's easy to understand, right? This is the CMS measurement of the top quark mass, and this is the Atlas measurement of the top quark mass. You know, it has slightly larger uncertainties because they're a little bit worse than us. but you want the common unknown value of this, and this is a fit to a constant. So you are fitting 2 points to a constant. You estimate the parameter of the constant. That is a special case of data fitting, which is combining 2 estimates of the same physical quantity, okay? All right, in fact, the tools that we use for combination and for fitting are the same. So I will have a few fundamental definitions, so it will allow us to touch base with things that you should know, but it's good to refresh our memory about these things. So the probability density function, we call it PDF, but don't confuse it with the PDFs of the partons inside the proton. They are also density functions, but they are probability distribution functions for special objects that they have different properties, okay? So the PDF of a random variable x is normalized to 1, okay? It's a function that you can integrate on the real axis, gives you 1, and describes the probability to find x in a certain range. So you specify the range, x plus the x, and you get the probability as f of x dx. And this is for a continuous distribution, but as you know, there are discrete probability density functions, such as the Poisson or the binomial, and in that case, this is a probability by itself. It's a point mass, what statisticians call a probability mass in a certain point of the parameter space, which is discrete, the number, the integer numbers, okay? Positive integers. So here you have the general case. This is a nice Gaussian PDF, and you get the probability that the value x is in a certain interval by integrating the PDF. Now, what is the expectation value? You know it because you have raised your hands, but anyways, this is the definition. You multiply the PDF by x, and you take the integral over all the real axis, and this is usually, but not always, defined as mu, okay? For a reason that we call this the mean of the distribution in some cases. And the mean depends on the distribution, of course, and it's the expectation value, because the act of computing the expectation value of x is to multiply that value by the PDF. So if you want to get the expectation value of a function of x, then you have to take the integral of the function of x. And so here, well, this e of x, you already computed it, it is mu. So you take the integral of x minus mu squared times the PDF. And this is the second central moment, because it's how much x departs from its expectation value. in squared. So it's the second moment of the distribution. And we call it the variance. All right? That is what the variance is. That is the definition of the variance. The variance is very important because it gives you a way to size up how fat your distribution is. Oh, okay, the mean of this distribution is mu, but really how much is free, is X free to vary around mu? How widely can it vary? Well, by a size that you will count in units of the variance, the square root of the variance, V. The variance has the property that the expectation value, so the variance itself, as you define it here, can be computed as the expectation value of X squared minus the mean squared. And this is an exercise that I leave for you this evening after dinner. Between 9 and 9:15, I will come and check if you're doing it, okay? Also well known is the standard deviation. The standard deviation is the square root of the variance. And this is our bread and butter. We always use the standard deviation colloquially to tell us, to brag about how small our intervals are. We say, oh, but my standard deviation is smaller than yours. Okay, one case when we don't brag about things being bigger, but smaller. Parameter estimations. So you want a big car and a small interval, right? Parameter estimation, the definitions of the parameters of a PDF. They are some constants that characterize the shape. So if I have a PDF of X, this might depend on some parameters theta, in this case, one single parameter, but there might be many. And for instance, this is the lifetime, or the parameter that governs the slope of a PDF. So this is a PDF, right? This is not a PDF. This is a PDF, okay? Please don't forget. Okay, so now suppose that we have a sample of values that are taken from this distribution. So we have a vector of values. We can ask ourselves, okay, I got these values. I have some counter, and I take the time after which I see a decay of a certain substance, and I get a nice distribution of exponentially decaying values, because this substance is decaying at a certain rate, and so the distribution should be exponential. And I want to estimate the lifetime, for instance. I want to estimate the parameters of this PDF. And I will write the parameter with a hat here on top to express the fact that this is an estimate. It's not a true value. It's an estimate of that. It's very different from the true value, okay? And it's estimated by plugging in this data in some machinery that spews out the number. We will see how these machineries are estimators and how we can construct estimators. So the estimator has this hat. It's a function of the data, okay? The estimate is the value that you get for the estimator once you plug in the data, okay? So two properties of estimators that you will always encounter are the variance, which we talked about, and the bias. So let's look at the estimator. The estimator, if we repeat an experiment many, many times, it will have its own distribution. So suppose that I take, I have 10 measurements of the lifetime, sorry, 10 values of time, okay, from 10 decays. And then I have 10 more, and then I have 10 more. These three are three different experiments. So I have a set of experiments. Each of these experiments gives me an estimate of the lifetime, and I can plot their distribution. Ideally, if I do it an infinite number of times, I get a nice smooth distribution of estimates of the true parameter, which I don't know where it is. It is somewhere in here, right? So the estimates themselves will follow a certain PDF, G, of the estimate given the parameter. The parameter we don't know, the estimates are those that come from these repeated measurements. And you see that here, I have three different distributions of the estimator, of the estimate, sorry. One is fatter than the other two. And of the other two, one is closer to the true value than the other one. So you see that these green and blue distributions are centered on the true value. That's good. That means that they are not biased. Instead, the red distribution is biased because it gets away, the mean is away from the true value. But which of these is best? Of course, the one with zero bias and small variance. But if you had to choose between the green and the red, what would you choose? Well, you need to do the math. And what is the math that you should be doing? You should add in quadrature the variance and the squared bias. This is called the mean squared error. And it's the best measure that you can give of how much off you are on average from the true value when you estimate this quantity many times. Okay, so the mean square error, I didn't put it in here because it belongs somewhere else, but that's what sums up variance and bias. So the bias is defined as the estimate, the expectation value of theta hat minus the true value. So do we know the bias? No, we don't know the bias because we don't know the true value. We can estimate the bias, okay? Anyways, if the bias is zero, repeated measurements will tend to the true value. If not, they will tend to B. But B itself might go to zero for large number of measurements, okay? So don't worry. Anyways, we want also small variance. That is a small, what is called a statistical error sometimes. Typically, the variance of an estimate is summarizing the stochastic part of the measurement, what can vary randomly. In the data set that you got, you have another data set, you have another data set, they distribute, and the variance is what tells you how much they distribute around. But the bias is the statistical way to describe the fact that you might have a scale, you weight yourself on the scale every morning, and it gives you a number, and you don't know it, but maybe all of these numbers that you get are off by 1 kilogram, say. That's a bias. If you care only about differences because you ate too much or too little, well, the bias doesn't count too much. But the bias is affecting your estimate of the weight. In statistics, we have this problem that small bias and small variance is something that you can never achieve. You can have small variance and then your bias grows large, or you can shrink the bias, but then your variance blows up. The variance-bias trade-off is ubiquitous in statistics, okay? And then we get to define the covariance and the correlation. So if you have two random variables instead of one, x and y, two random variables, you can define their covariance, which is defined with an expectation value. The expectation value of x minus the mean of x times y minus the mean of y. And this is, you can expand this expectation value. You know, we are implicitly integrating over the PDF, etc. But you can prove easily that this is coming up as E of x times y minus 2 times, well, this is just an equivalency, but when you expand and you get minus 2 mu x times mu y, the expectation value of mu x is mu x, and the expectation value of mu y is mu y, because they don't depend on x and y. So this comes out of the expectation value symbol, and then you have plus mu x mu y, which also comes out. So that is basically what you come out with. All right. So it is the expectation value of x times y minus mu x minus mu times mu y. This, as you have noticed, this is not a single expression, but you can have multidimensional data, and then you have matrix elements. So you have many different components of a matrix, which becomes the covariance matrix. So the covariance matrix for two single values, x and y, you will have a 2 by 2 matrix. But if you have the covariance matrix of many different variables, it may grow very large, okay? So the diagonal elements of this covariance matrix are the individual variances of the two random variables x and y, sigma x squared and sigma y squared. But you also have non-diagonal terms, sometimes. Not always. Sometimes these values will be 0, and that is very nice, because if those non-diagonal terms are 0, that means that the two measurements x and y do not affect each other. They don't talk to each other. They are independent of one another, okay? Well, we'll get to that, how much independence and correlation refer to one another. The correlation term here is called R, and it's a correlation coefficient that you put on in front of the product of the two square root of variances, sigma x and sigma y. You see this matrix is diagonal, okay? And okay, so you have some correlation governed by a number which is between -1 and +1. This number is called correlation coefficient. So this is what the correlation coefficient measures, how much the two variables talk to one another. And this is basically defined here as in the previous slide. Now, if the two variables are really independent, that is that x and y are, you can take the PDF, the density function of x and y separately, and you can decompose it into the product of two different PDFs, f of x and f of y. If you can do this operation, then not only the correlation coefficient is 0, but also you have that the expectation value of the product is the product of the means. And the covariance matrix is diagonal, okay? So if they are independent, then for sure the correlation coefficient is 0 and you have this equality. But the fact that the expectation value is the product of the expectation values of the individual random variables, that is not sufficient for them to be independent. So independency is a stronger condition than 0 correlation coefficient. We have to be careful when we speak of uncorrelated variables and we actually imply we want to say that they are independent. Because in statistical terms, independency of two random variables is a much stronger condition than the correlation coefficient being 0. And here from Wikipedia, we get a nice graph which shows you what the correlation coefficient of two variables along the x and y axis, ideally on these graphs, not depicted, but okay, you can imagine the x-axis here and the y-axis there. For each of these clouds of points, you see that the correlation coefficient of points that stay on a line, regardless of the slope, but not for zero slope, because this y is a single value, then you don't speak of a correlation. But you don't even have a correlation coefficient in that case. But all of these dependencies are very, very clear and linear. They are correlation coefficients of 1 or -1, depending on whether the two parameters have positive correlation. So, sorry, if the derivative of one has the same sign of the derivative of the other. Okay. But then you have all these interim cases where the correlation coefficient is large or smallish or null. You see, when you have null correlation coefficient, the two data points, the points spread out in a way that looks like one of the variables doesn't affect the value of the other. But you see that you can have cases when the correlation coefficient is 0, but there is a very striking dependence between the two variables. So for instance, you can have data that stay on a circle. So the value of x conditions a lot the value of y and vice versa, but the correlation coefficient is 0. So these two variables are not independent. They don't stay with the same probability on the plane, but they are 0 correlation coefficient, okay? And then we get to discuss the error ellipse, which is an important construction that allows you to visualize the correlation between two variables, the variances, so that is the square root of the variances of the two variables, and a few other things. How do you construct this error ellipse, which is for 2 dimensions, but we are much bolder than that. We do fits in hundreds of dimensions sometimes, so it boggles the mind to think at the kind of shapes that we have in this 100-dimensional space, but the construction is valid for whatever number of dimensions, at least the essential parts of it, okay? So let's take, instead of x and y, we talk about theta j and theta I, okay? 2 parameters theta. And when we measure these parameters, and we measure it with lots of data, in the large sample limit, everything converges to a Gaussian distribution. So we can discuss this in abstract by saying that we have large data sets, and the estimators distribute according to a 2-dimensional Gaussian distribution, which you should imagine here. I cannot do it on a PowerPoint slide, but you should imagine this to be a Gaussian distribution, okay? All right, in 3 dimensions. So this is a 2-dimensional bell-shaped distribution that describes the probability to find an estimate of theta j here and an estimate of theta I there. So any point of the plane has its associated probability, the height of this curve. So you should think of it that way. And and sorry, this is centered on theta 1, theta 2, not q, because the symbol got away. So you can draw an ellipse which captures a certain integral of this PDF. What I'm saying is that it captures 68.3% of the integral on the full plane of this 2-dimensional distribution, where the chi-squared, I don't know why the symbols have gone away here, the chi-squared, we will define it later, but okay, there is a certain measure that tells you how far away you are from the mean of this two-dimensional Gaussian, which is the center of this axis here. And this defines the standard deviations of the estimates of theta j and the estimate of theta I, okay? So this defines this curve, which is basically a isoline at equal height of this Gaussian two-dimensional distribution. And this distribution, actually in 2 dimensions, I correct myself, it will not capture 68.3% of this integral. It will capture much less, because in 2 dimensions, the 1 sigma times 1 sigma interval is less than 68.3%. In 1 dimension, it's 68.3%. But this construction allows you to draw a curve, anyways, at 1 sigma. You could draw a curve which is larger that will capture 68.3%. But that's not the point here. The point here is to look at the interrelation of these various quantities that we have here. So the correlation coefficient between the 2 variables here geometrically is the ratio of this distance to the full theta sigma I. So you take the tangent of the ellipse, the vertical tangent of the ellipse at 1 sigma, and this defines this point, and this point defines an ordinate, and this distance is rho times the full sigma I, okay? So it might be hard to see, but if you have a less correlated situation, this tangent point will lie at a point which is closer to the center line, and so this correlation coefficient is a smaller fraction of the total sigma, okay? So you see that rho here is the ratio between these 2 lines. In this case, is small. In that case, it's a little bit larger. If I have a very correlated situation, the ellipse will be like that, and the tangent will be basically equal to this distance. So basically, the correlation coefficient will be 1. All right, so that is the geometrical reason for rho. And then you have another thing, the location of the tangent to the axis, these 2 points define this dotted line, and this, this dashed line. Maybe I misstated this, wait a second. Oh no, sorry, I was saying 2 different things. Okay, the location of the tangents define these standard deviations along the 2 axes, okay? Instead, then you have an angle phi, which is the axis of the ellipse, and this angle phi has this definition, which you can compute, and you can actually verify at home. Do this between 9:15 and 9:30 in the evening, please, this evening. And since I've been told to give you exercises, okay? So this is a joke. I mean, I don't think you want to spend your time deriving this equation. But the point here is that this construction has certain properties that will become interesting later on when we do chi-square fitting. So when you measure a parameter, for instance, you measure theta I and you get theta I hat at this point, not this one, which is the center of your distribution of theta i's and theta j's, but you measure one parameter, you can get an estimate of the other one by taking a point along this green line and seeing where it intersects here, and you can read out the value of the other parameter. So you can have a measurement of one parameter when you fix the other by taking this intercept here. And the uncertainty on that single measurement is this sigma inner, which is sigma times the square root of 1 minus the correlation coefficient. So what that means is that when you have a certain correlation between two variables, a measurement of one variable at a specific value fixed of the other variable is affected by an uncertainty which scales down with the amount of correlation. This is what the correlation coefficient does for you. It decreases the uncertainty of your measurement when you are fixing one of the two variables. Since they are correlated, fixing one of them is affecting the other one. And so the other one will shrink its uncertainty, and this is geometrically this quantity sigma inner. Because you see, if I take a value of theta j fixed here at the center, and I measure theta I will not have the full variability given by the sigma, but it will only be able to vary according to this segment here, which is given by sigma inner. Okay? And so in that case, we may report the value of one estimator at the value of the other, and the slope between the two is basically this, given by this ratio of variances. Okay, so this is the sigma, the case for two variables, and you see that it's already pretty complex. I mean, you have the two variances playing out how the two parameters depend on one another, and you have to be careful in extracting the information that you want. So when you have many parameters, this becomes really complicated, okay? And the way out is to rely on Taylor expansion and stop at the first term. That is to say that you can do error propagation by taking the same, take this situation. You have a certain number of identically distributed and independent variables. That's what you have in the textbook. IID means that they are independent and that they are what?
Identically distributed.
Identically distributed, yes. So Xi. So you don't know the PDF, but let's say that you know their mean and you know their covariance matrix. And let's say that you have a function of the X, and you want a PDF of this function of the X. You have the PDF of the X, and you want the PDF of the function of the X. And you can expand in Taylor series by stopping at the first term, which is this. It's the sum of the derivatives versus the xi's times their difference from the mean. If you use Taylor series expansion, you can show that the expectation value of y and the expectation value of y squared, from which you can get the variance of y, which is the function of the x, can be determined simply by these formulas. The expectation value of a function of x is a function of the mean, and the expectation value of the square of the function of x is this more complicated expression. So you have a way to deriving the variance of a function of the x if you know the function, the variance of the x themselves. So you can propagate uncertainties on x to derivatives, not derivatives in the mathematical sense, but to other quantities that you can construct with x. And that is what we do basically without thinking when we propagate uncertainties and sum up sigmas in quadrature, and we use the typical formula that you want, for instance, you want the variance on some function, and you do the derivative of the function times the derivative of the variance of the variable, right? And you can do this for any terms depending how much x depends, f depend on x. So this kind of formula derives from this. And this becomes a little bit more complicated if you have a set of functions, now y is a vector of the random variable x, which can also be a vector, and you can still build the covariance matrix of these functions as this more complicated formula that involves the partial derivatives of each of the y over each of the x, okay? And you have a sum over all the indices when you evaluate the x at their respective means times the covariance matrix. And this can be expressed in a matricial form if you have a matrix of derivatives that compactifies this notation. Then you have in simple matrix form the covariance matrix of the y given as a function of the covariance matrix of the x multiplied by these vectors of partial derivatives. Okay, this is boring mathematics, but you need to see it at least once, right? So these formulas allow you to propagate the variances from the x to the y. But this formula is an approximation. Please don't forget. It is based on having taken a Taylor series expansion, which, you know, is an approximation because you stop at a certain level. In fact, it's stopping at the first term. So, and this is only valid if this expansion, linear expansion around the mean of the x can work if you have smooth functions, but can be tricky if your functions are not smooth, okay? So be careful. So you have, every time you use some error propagation formula, you have to have a coprocessor in the back of your brain that says, okay, I have to keep in mind that this is an approximation and it may be wrong. Okay, and it's only good to report the result if I say exactly what I'm doing. You have to keep checking these things, okay? So we want to express now the covariance matrix of the function of the data. We use the Taylor expansion, and then we can evaluate the expectation value of y squared, which turns out to be this expression, which is a little bit ugly. And this is the full mathematical blow up of this expression. And that simplifies because the expectation value of y of x is y of mu. These things simplify a little bit, and you get this expression that we saw. And we get finally the variance of the derived quantity as the formula we were seeing before, the expectation value of y squared minus the square of the expectation value of y, so minus the mean squared. And this is basically this expression here. So we now have a practical way, and you see this is basically the same thing I draw here for a case of a single variable. So we have a way to compute the errors on the derived quantity. So to see how this formula works, let's take it in a very simple case. Let's take in the case where the two variables are combined in doing their sum. So why now be the sum of two random variables? The simplest case you can take, okay? I'm not taking it hard for you on purpose. Let's take the simplest possible y that you can think of. Given two variables, x1 and x2, then by applying the formula, the variance of y is equal to the variance of x1 plus the variance of x2 plus twice the cross terms I different from j. Right? From this follows directly. And this is very nice, in particular, if you have no correlation, because if you have no correlation, this term disappears, right? The off-diagonal terms disappear if x1 and x2 are not correlated. And then the error on y will be, the variance of y will be the sum of the variances of the two addendums. When you have a product, though, the sigma y squared will be a little bit more complicated because when you derive one value, you get the second one. So you will have this expression, which is a little bit more complicated, but if you divide now by y itself, which is x1, x2, you get the relative variance of y, sigma y squared divided by y squared, is now the sum of the relative variances of the x1 and the x2 plus the covariance terms, the correlation terms. So let's compare these cases. Now you see that in one case, if you have no correlation, you add uncertainties in quadrature. You know that, right? And if you have a product of various different factors, it is the relative variances that add linearly, all right, in case of no correlation. So this is important to note, right? It's good to keep in mind and it will help your calculations. All right, so I want to give you one example of what you can do when you can see through these calculations and actually I have another coprocessor here that can compute the variances of functions of your random variables. So we have seen this formula, and we don't pay much attention to it, we just use it, okay? But if you can read into this formula a little bit more, you can actually get something out of it. So let's take the example of taking two measurements with a very old-fashioned scale of a certain object. You know, this scale is particular in that you have reference weights of different value that you put on one arm. You can put them anywhere anyways, and you can put your object on one arm, and you can find an equilibrium point, and then you can measure, sum up the weights you had to put in order to create equilibrium, okay? Now, let's imagine that you have two objects, A and B. And let's say that the smallest of these guys weighs 1 gram. That means that no matter how you arrange these reference weights, your accuracy of the measurements will be 1 gram. So let's say that it costs you to make measurements. Let's say that you have to give me €1 or 10 rupees, I don't know, for one measurement. So, and you can only do two measurements because you have 2 arrows in your pocket, and you want to weight the two objects. What do? Well, I have two measurements, I have two objects, I proceed, right? I weigh A, and then I weigh B. No, somebody already knows. So, except from him who already knows. Do you have another idea on how you could proceed? Well, okay. There is a better method, and it has to do with error propagation being applied, even if unconsciously in the back of the other processor here, I don't know. If you weight separately the two objects, your results will be affected by the stated accuracy of the scale, so you will have uncertainties that are exactly 1 gram. That's what you paid off for. You paid €1, you get an accuracy of 1 gram on the weight of A and on the weight of B. But if you know error propagation, you might come up with a better idea. You put the two objects on one plate and you weight them, and then you put the two objects on two different plates and you find equilibrium again. And you are effectively weighting the sum and the difference of the two objects. And if you weight the sum, you get an accuracy of 1 gram. You weight the difference, you get an accuracy of 1 gram. And then A has an uncertainty which is given by this expression, which is 0.71 grams. And B is also the this is the semi-difference between sum and difference, and this is the semi-sum between sum and difference of the two weights, and you get 0.71 grams. So how is it possible that with two measurements you get a smaller uncertainty? It is possible because you are letting both objects participate in the weighting, and they affect the two measurements of sum and difference. So you have made optimal use of the available information and of the instrument that you have. And you have only been able to do this because you were able to exploit how error propagation works. And basically, the rationale behind all of this is when you are weighting one object, the other one is left on the table and is asking you to participate, but you leave it alone, okay? Instead, if you let it participate in your measurement, it affects the extracted information. All right, so this is a very stupid, silly example, but it illustrates the point. Error propagation works and gives you a lever with which you can extract better information. Yep. Just one. Just one. Yes. No. What is same? Sorry. S is the sum of the two measurements of the two objects. So basically, I have only made two measurements, but in one case, I have put the two objects here, and I have found the equilibrium point. And so I have measured basically the sum of these weights of reference gives me the sum of the two objects' weight. And then when I do the difference, I will put one object here and the other here, and maybe I will have to put some reference weights here. So this is A and this is B. This is A and this is B. And in this case, I get the difference of the two weights. Only one measurement in each case, and it's not an average, okay? But each of these estimates is affected by an uncertainty, and the uncertainty can be computed by error propagation. All right. Or you could ask yourself what happens instead if instead of a constant error of 1 gram, the balance provides measurements with an accuracy of some percentage, 1%. The problem changes then because error propagation changes. You have a percentage error, so you are in multiplicative regime. So if we do two separate weightings, of course, each of them is affected by 1%. So 1 kilogram plus or minus 10 grams, 2 kilograms plus or minus 20 grams. If we take the sum and the difference, this time we do the math and we get that the uncertainties are equal, as in the sum case, but remember, if the two objects are different in this case, the uncertainty of the individual measurements would be different. 2 kilograms plus or minus 20 grams, 1 kilogram plus or minus 10 grams, because the uncertainty now scales as a fraction of the total weight. But the procedure of getting the sum and the difference has shared equally the uncertainty, because now both are equal to k square root of the two objects squared divided by 2. So basically, instead of having ka and kb, here you have the square root of these squares. So if the two objects have equal weight, you have not done anything, of course. But if they are very different, we can gain accuracy on the heavier object at the expense of lower accuracy on the lighter object. And this might be practical, who knows? Okay? The limiting case of one weight being much, much heavier object than the other object corresponds to a very inefficient measurement of the lighter object because it basically blows up the uncertainty on the lighter object, but you get basically to weigh the heavier one twice. In this case, with a square root of 2. Okay, so now that we are talking about weights on a scale, we can go and talk about weighted averages, and I think it's a good time for a little bit of water. All right, so now let's go back to our issue, right? The top quark measured by CMS and the top quark measured by Atlas. And let's get to discuss how we really do it. We were saying that this is a fit. Okay, it is a fit. But in statistics, the way to handle this is doing the weighted average of the two measurements. Why weighted average? Because the two measurements are different uncertainties, so you want to give more importance to the result with a smaller uncertainty. So let's take these measurements to be x1 and x2 of the same physical quantity x0, the true top quark mass, with a certain uncertainty sigma 1 and sigma 2, okay? This basically is saying that I assume that the distributions I'm sampling these values from are Gaussian, okay? Gaussians with mean x0, the unknown value, and with sigma I. And I'm also implicitly assuming here that there are no biases here because I am centering the two Gaussian PDFs on the true values. If there were a bias, it could have appeared here because I would have said, I measure, CMS is measuring the top quark mass, but if the true top quark mass is here, CMS is measuring it here because it has a scale uncertainty or some bias of other kind, a systematic that offsets it. So I would write the measurement of CMS as X CMS of mass of the top plus the bias and sigma of CMS or something like that, okay? But it never happens because CMS doesn't have this. I'm sorry. Yeah, so you always have biases. And you can try to estimate the biases, and that is a second order correction, but let's leave that alone now. So we wish to combine the two measurements linearly. Why linear? First, well, what is happening here, I don't know, but yeah. So this question can be answered by a minimization procedure, which will involve what? Taking a derivative, right? And setting it to 0, of course. But first of all, we can define our average as C times x1 plus 1 minus C times x2. Why do I do this and substitute D with 1 minus C? Well, you should think about the fact that you want the average value to converge to the true value, and you can reason with expectation values, and you will find that you have to have this factor that the sum of C and D is equal to 1. So you write this explicitly in your combination formula, and then what you do is proceed to minimize the uncertainty on the derived factor x. And since x depends on C, what do? You take the derivative of that. So first of all, you write the variance of x, which can be expressed from the variances of x1 and x2 by error propagation. The formula is here, right? And you get sigma squared of x is C squared times sigma squared 1 plus 1 minus C squared times sigma squared 2. And now we find C by taking the derivative of sigma x squared over C. And if you take this expression and take the derivative with respect to C and set it to 0, you will find this value for x and this value for sigma x squared. That is to say, you will find C times that the derivative of this is 0, and then you substitute in these two expressions and you get these two expressions, 930 to 945, okay? So these formulas I imagine that many of you have used several times when you do the weighted average. I mean, you should know them by heart. They are very simple to remember. You look at it, every measurement gets a weight which is the inverse of its own variance. So x1 I divided by sigma 1 squared, x2 I divided by sigma 2 squared, and then at the denominator, what do I have? I have the sum of these weights. And the variance of the combined measurement is 1 over the sum of the weights. So it's very easy to see that if one of the variances is much smaller than the other, so for instance, if the variance of CMS is much smaller than the variance of Atlas, as is always the case, then you will see that what happens is that at the denominator, one of the two factors dominates over the others because you are dividing by that small number and you will get a larger addendum than the other, and then you will divide by the sum of the weights where one of the two will dominate over the other. So in the limit that one of the two variances is much smaller than the other variance, it is that particular value that dominates and you get a weighted average which converges to that value. All right, I think it should be clear from these mathematical expressions what is going on here. Do you have questions until here? You can also ask later, but if something is not clear about the simple weighted average, you better spill your guts, because now we are going into correlations territory and that will be ugly. Okay. Okay, so all is clear here, right? I have applied error propagation, I have taken a derivative, I have extracted the weighted average. And this is a simple exercise. We will get back to this with correlation, but let's first discuss some definitions. Actually, I think, I don't know if we will get to the case of correlations today, but well, we'll see where we get. So estimators, we touched on the definitions at the beginning, but we didn't really get into the heart of the matter. So let's give a sample of data, n observations of some random variable x that are drawn from a certain distribution function f. What is a statistic? Is a function of the data. The function of the data that you have that contains no unknown parameters. So once I have the data, I can construct the tested statistic. My statistic is a function of the data that I can compute straight away. Okay, this is the definition of a statistic, a function of the data. And then an estimator is a statistic which is used to estimate some property of a PDF, some parameter of a PDF. And when you use it on a set of data, provides the estimate. Okay, we said that already. And we said also that estimators are labeled with a hat, but sometimes I am lazy, so I will use this sign. One property of estimators that is important and that we will touch on later is that estimators are consistent if they converge to the true value when I throw at them a large amount of data. So an estimator can be consistent or not. It is consistent if by having large data sets, at the end it gets to the true value, right? So this is asymptotic behavior. We almost never are in that situation, but we would like our estimators to be consistent to begin with. But sometimes we will choose estimators that are not consistent for some reasons. I don't think we will get there, but okay. and then you can have the expectation value of an estimator, and you can take the estimate and multiply by its sampling distribution. So one example of an estimator that you use day to day is the sample mean. The sample mean gets written with a hat, okay, because an estimator, and it is just a statistic, you see, a statistic that doesn't depend on parameters, it's just a function of the data that you got. And the sample variance, S squared, is the sum over of the squared deviations from the estimated value of mu, and it is multiplied by 1 over n minus 1. Okay, so this is an unbiased estimator of the population mean. What it means is that you have computed an estimate of the mean, and you plug it into this variance expression that is an estimate of the variance, okay? But it is unbiased, and to make it unbiased, you have to take this n minus 1 correction. And I think we will discuss this in more detail later. But these are just two examples of estimators that you can construct. They are functions of the data, okay? We said what the bias of the estimator is. Here we say it formally. We write the bias as the expectation value of theta hat minus the true value. So if the expectation value of your estimator is off from the true value, you have a bias. And you can be consistent even if you are biased, because you can, this expectation value will tend to the true value as n tends to infinity, but still you can have, with finite n, you may always have a certain bias, even if you try this experiment many, many times. So you can have a bias when n is finite, and the bias can go to 0 when n goes to infinity. So the estimator is consistent because in asymptotic limit converges to the true value, but in all practical instances, you will have a bias from it. Other important properties of estimators. Efficiency. An estimator is efficient if it is the one with minimum variance within a certain class. So you can have different estimators of a certain kind, and the efficient one among the class is the one with minimum variance. An estimator can be robust, and we will see a practical example in the opera experiment later on, when the estimator is less dependent on the true distribution from which you're sampling. What do I mean by that? Is that I can construct an estimator by assuming that the data are sampled from a Gaussian PDF, but actually the data are coming from a box distribution or some other distribution. And if I showed you before that if you get the distribution function wrong, you can be very wrong with your results, right? Remember the compound Poisson versus the simple Poisson. But there are estimators that are robust. That means that they are not very much affected by how you sample the data. They don't depend so much on whether there are fat tails or short tails in your PDF. And there are instead estimators that are very, very picky and that will become very biased or very wrong if you are mistaking the sampling distribution. So an estimator which is robust is a good thing to have, particularly when you don't know very well the model that you are sampling from. In particle physics, we never know our model. We know that, okay, our protons come in and a quark will come with a fraction, the Bjorken fraction x will be distributed with a certain value, but we don't know that very well. It's a model, and the model can be wrong. Actually, all models are wrong, and some are useful. But robustness, therefore, is very useful for a physicist, okay? And we can study this with experiments, and we can find out that some estimators are better than others because of that. And well, okay, simplicity is another property which I don't want to get into. I told you about the mean square error, which is the sum of the variance and the square bias. And this is the quantity we'll want to minimize in your practical experiment, because it really summarizes how much off you can be in your measurement with respect to the true value. So if you have a bias, you want small bias. If you have large variance, you want small variance. You cannot constrain both, but you can probably find a middle ground where the sum of these two squared terms is the smallest. It is typically, since we are talking about machine learning in this school, it is typically the case that you can have the mean square error as the loss function in a machine learning task. Because it's a very good, in a regression task, it is a very good way to assess how well you're doing, okay? Variance plus squared bias. Yeah. And then you have the Rao-Kramer-Frechet bound, which I have another slide for, and we'll get to that once we define the likelihood. But okay, you have a way, but you have several ways, in fact, by sampling and others, that can tell you what the variance of estimators is. So, and you can choose an estimator based on how much bias they bring in and what kind of variance they promise to give. And I don't want to bother you with too many definitions, because I guess you are longing for lunch, but there are a few here that you can go over probably offline. We will go through the definition of the maximum likelihood estimate and the least square estimate. These are the methods of the maximum likelihood and the method of chi-squared, okay? And we will go in the depths of these two methods in a minute. It's also interesting to say that most estimators are unbiased and normally distributed, but in asymptotic regime where your data is large, these quantities are possessed by most estimators that you can think of. But the problem is that typically we are working with small samples, and then it really matters to choose the best estimator. All right. So let's discuss the maximum likelihood estimator. You can take a probability density function for a random variable, a Gaussian, I don't know, whatever. So a function which is normalized and that describes how the data distributes with a certain parameter that, that we don't know about, okay? Now, the method of maximum likelihood gives you a chance to estimate the parameter theta. If we have some data that are sampled from X, so we get information about theta from the data because the data come with a probability which depends on theta. The probability of the data depends on the PDF, okay? This is the probability collectively of having observed the set of data n, because basically it's multiplying the probability of each single observation xi, okay? So you observe, you take a measurement, you observe the lifetime, the decay time to be 3 plus or minus 0.1 seconds. You look up the PDF, it says it's 0.03, okay? Then you take another measurement, it's 0.7 seconds plus or minus 0.01 seconds. You look at the PDF and it tells the probability is 0.7. And so you integrate, you multiply all these probabilities and you get their product. This P will collectively tell you how likely it is that you collected this set of n measurements of this decay time or whatever it is, okay? It will be a small number, but it's because it's a product of small numbers all between 0 and 1, okay? But then what you do with these p's is that you can consider them to be a function of the parameters. So the likelihood function is a function of the parameters of the PDF. And it's only possible to write a likelihood function once you have the data. You cannot write a likelihood function if you don't have the data, because you don't have the probabilities, you don't know anything, right? But the data allow you access to the parameter. It's a function of the parameter. It's not a PDF. These are the PDFs, which you can integrate by intervals dx, okay? The likelihood function is a function, it's not a PDF. When you have the likelihood function, you can define estimators which will do the job for you. They are the solutions, theta hat, of the equation that maximizes the likelihood. This is finding the extremum of the likelihood function as a function of each of the parameters. Again, when you have a problem of maximization or minimization, you take a derivative, right? And you take the derivative of a likelihood function with respect to each of the parameters, set them to 0, and you get estimates of the parameters. You can see from this construction that the likelihood function is requiring you access to the PDFs of the data. This is in contrast to what we will see with the chi-squared method, which assumes that everything is Gaussian. The likelihood knows and exploits your knowledge or your assumption of what the PDFs are, that the data that you have are coming from. Okay? So the simplest way to estimate the variance of your estimates of the parameters from the maximum likelihood method is to take the inverse of the negative of the second derivative of the log likelihood function with respect to the parameters at the value at which you're measuring. So this is basically, this is a recipe, but I think we will fiddle with this expression when we do some practical exercises later on. And it is this expression, which is what the Minuit fitting program returns when you invoke migrad. Migrad is a routine that was written in the 70s by Fred James and collaborators that will basically compute this for you when you maximize a likelihood numerically, okay? But you can compute this numerically yourself. Actually, we are going to do this in a moment. This, however, should be understood to be a lower limit, and it is worth, it is valid when you have Gaussian PDFs. When you have distributions that are not Gaussian, typically the variance estimate has a larger value than this lower limit. This is enshrined in the Rao-Kramer-Frechet inequality, which tells you that the variance of the estimates that you have is 1 plus something, but let's leave this alone for a second, 1 over the estimate, the expectation value of the negative of the delta squared log likelihood with respect to theta squared. So you see that this expression is equal to this one only if you have 0 bias. Only if the derivative of the bias with respect to the parameter is 0 in practice. Okay? So, and it is a lower bound, okay? If you have very complex PDFs, this is certainly larger than this expression. Now, and that's where I think instead of having lunch, you could do some calculation with paper and pencil. The loaded die example that I've cooked up for you. Imagine that you have a die which has 6 sides, right? And on each side you have a number 1, 2, 3, up to 6, okay? And you throw the die and you get a number, which is the one that is showing on top. And typically the probability of each number to come up is 1/6 if it is a cube. But if you are gambling with this die, maybe you can paint with lead paint one of the sides, and then that side will typically fall on the ground more frequently. So this is a loaded die, and it's a way to trick when you play for money, right? So let's take a model for how a loaded die could have probabilities. And let's say that the probability of 6 get boosted by some number, t. It is slightly larger than 1/6. And since the 6 is on the opposite side of the 1 in your cube, the 1 will get damped down by a little bit, but not by the same amount, because also the other sides get damped down by a small factor. So this is a model, right? It's not the truth. Even if you paint 100 times your die, you will never get that the probabilities are exactly those. But it's a model that just describes what could happen if you have a loaded die. And we will test this model by assuming that we throw the die 20 times and we get these results. You see that we get 1 3 times, a number between 2 and 5 3 times, and we get a 6 5 times. So we have gotten 5 times a 6, which is more than you expect. Because on total you did 20 trials, you should have expected what? 3.33 I'm cooked up myself. 3.33 times a 6. How can you determine the load on the die with this data? Well, the load is affecting the PDF, and you have data. So you can construct what? A likelihood function, because you have the PDFs. So here I'm already giving you it, and this comes up 3 times the logarithm of 1/6 minus t halves, because this is the probability of 1, minus 12 times, because I have 12 die throws that give you 2 to 5, and this is the probability of that, minus 5 times the probability of a 6, which is that. Okay, so I have this expression, and I can proceed it to maximize the minus logarithm, minimize the minus logarithm, which is to maximize the likelihood. And I do this by taking the derivative of this expression with respect to t and setting the derivative to 0. Fifth grader math, and you get a quadratic expression in t, and you can solve for t. And there is only one solution in the allowed range for t, because of course the probabilities that we have defined there before are only valid if t is in this range. And we get t, our point estimate, as 0.072. So this is our point estimate for the load of the die. And you see that it is a positive load because we got more 6s in our data than we were expected to, 5 with respect to 3.33. As we expected. Now we can compute the uncertainty and the variance by getting the variance with the Rao-Cramer-Frechet lower bound by taking the inverse or the negative of the inverse of the second derivative of the log likelihood. And this amounts, if you do the calculation, to 0.084. Sorry, this is the square root of the variance. So we have 0.072 plus or minus 0.084. So we have a load which has an uncertainty, and it is, if we look at the value, it's compatible with 0. So we cannot establish the presence of a bias, of a load on this die from this example. But maybe if we threw the die 1,000 times, we would have been able to detect even a smaller bias, okay? So this is a simple, nice example of something that you can compute by hand. You can do this at home, but you can also do it on some other example. I will have another example later on. But the point is that you should do it once in your lifetime, okay? Solve a problem by maximum likelihood with paper and pencil. If it is continuous distributions, it's complicated, but if you have discrete distributions, like this, it's actually not so hard. And actually, the challenge for you would be to write a computer program that does the following. And this you can do from 9:45 to 10:30 this evening. See, I'm scheduling your evening tonight. So you can write a root macro that determines using the likelihood. So you don't have to do the math if you want to do this with root. If you like to code, you take this expression actually, and you will have also to have access to the probability distribution functions to generate the die throws in your toy Monte Carlo. You do a toy Monte Carlo that you will call die.c, and it will have a function that is called die of n, and you will input the number of throws that you want the program to do by looping from 0 to n minus 1, storing the result of a call to a random number generator multiplied by 6, or from 0 to 6 added to 1. So it will generate numbers from 1 to 6, okay? And then you will compute the number of occurrences of ones, of sixes, and of other results. And with those, you can compute your likelihood and the derivative of the likelihood. And you print out the result. So doing basically what we did in the previous slides. Why is this interesting? It's interesting because once we have this tool, we can encapsulate this function in one that generates data when t is different from 0. And we generate the data with many, many different values of t, spanning from minus 1/6 to plus 1/3. And so we will be able to see how the likelihood tracks the true value of that we have inputted in the PDF. And so we will see how consistent and what are the properties of the likelihood estimate that we have of this true value. But more importantly, it will give us access to the lower limit on the variance of our likelihood estimate for t. And so we will be able to spot the coverage properties of the likelihood intervals. And this will be the subject of tomorrow's lecture, but the program, we can build it up until we can actually get nice coverage plots. And we can do also hypothesis testing with it. So you see, by building up with a very simple example that you can cook up in a second, you can actually go on and study the properties of estimators and of intervals. So it will be actually interesting, okay? And if you don't have the time from 9:45 to 10:30 to do this, you can actually download the code from my area. But for now, the question could be, how frequently do you get a result for t that is less than 1 standard deviation away from 0? Already this sounds like coverage properties, because you should get 68.3%, but you will not get 68.3% in all cases. And I think we can stop here and have lunch and come back for the rest. But first, I would like you to think of all the possible questions that you would like to ask me during my lunch, because I will be eating. I will not answer your questions.
Okay, so we can take some questions if you have. Okay, yeah. So do you have mic nearby?
I'll. Yeah.
Yeah, so this error ellipse is one of the planes when we slice up the binormal distribution into variables, right?
Yeah.
So this plane
Like
of
ocean, yeah.
yeah. So this plane, is it like parallel to the plane of the variables?
Yes, basically, basically, I'm looking at this PDF from above. I will try to make a. That's okay. Yeah, so let's see what my three-dimensional drawing capabilities are. So this is variable x1 or theta 1, this is variable x2 or theta 2 or whatever. And then you have a certain marginal distribution for x2, which is Gaussian, a certain marginal distribution for x1, which is also Gaussian. And then you have your PDF, which is basically a two-dimensional distribution, okay? Sorry, I'm looking at it from here. From here, it might actually look very weird. But basically, what you have is an ellipse in this plane of the two variables that will define an axis here, and that is what you are seeing in that graph. And I'm cutting this two-dimensional distribution at some point because each of the two marginals is a Gaussian, and it has a certain sigma, and I'm taking the one sigma interval, one sigma interval on each of these two. So from here to here, and from here to here, and basically this becomes this ellipse.
But this does not guarantee that the ellipse will sort of be parallel to the plane of x and y, right? If I'm cutting it with respect to sigma x and sigma y.
It's the two-dimensional distribution is on the z-axis, okay? So you should think of it as a distribution that extends this third dimension, and I'm cutting it at a certain point which projects on the plane like this.
Okay.
But it's an infinite distribution.
Okay.
Okay.
Thank you.
The plane is by construction parallel to the x.
Yes.
That's what.
Yes.
More questions here?
Okay.
Thanks, Thomas.